Hi there, my name is Andrew Brown, and welcome to Nucleophiles, Electrophiles, and the Leaving Group. This video will introduce various representative classes of nucleophiles, electrophiles, and leaving groups, but it will also investigate the effects of various solvents on nucleophilicity, namely, and will culminate with the nucleophilic substitution reaction. After watching this video, you should be able to answer questions like this one, which asks you to predict the missing reactant in a nucleophilic substitution reaction identified only by the hybridization of its intermediate. Before we dive right into the nucleophilic substitution reaction, we're going to define the types of molecules involved so that we can better understand the organic chemistry at work. A good starting point is the nucleophile. The term nucleophile is actually a combination of Latin and Greek, with nucleo referring to an atom's positively charged nucleus, and phile coming from the Greek to love. Thus, we define a nucleophile as a molecule with plenty of electron density. In fact, its very name owes to the attractive relationship between negatively charged electrons and a positively charged nucleus. The most straightforward representation of a nucleophile is the anion. With a circled negative symbol next to the anion's name, these molecules appear to be almost begging to form a bond with a nearby positive charge. Double and triple bonds pack in extra electrons within their pi bonds, increasing the electron density of the molecule without altering the connectivity of the atoms. As do lone pairs, which are not usually included in the molecular formula. As you look back at the three classes of molecules here that made good nucleophiles, notice that each class represents a different strategy for increasing a molecule's electron density. In general, something that is a good base will also be a good nucleophile, as in the example of the hydroxyl anion here. However, just because something is a good nucleophile doesn't guarantee the converse will be true. It gets a little beyond the scope of the MCAT, but the basic reasoning here is that nucleophilicity is determined by the energy associated with the intermediate in a reaction, while basicity is determined by the energy of the products. Let's take a couple minutes now to review how nucleophilicity is affected by certain aspects of the reactants themselves, or the solvent. When the negative charge associated with the nucleophile increases, we can envision its nucleophilicity, or how good a nucleophile it is, also increasing. Therefore, in the example of a hydroxide anion compared with water here, we would expect the hydroxide anion to be a stronger nucleophile. What about electronegativity? That's a bit different than negative charge, and as it increases, nucleophilicity will actually decrease. To understand this phenomenon, it is helpful to look at the halogens as an example. While fluorine is the most electronegative, its valence shell is also very close to the nucleus, meaning that its electrons are bound tightly and are not largely available to form bonds. The valence shell of bromine, by contrast, is located much farther away from the nucleus, so its electrons are more free to bond. The next factor affecting nucleophilicity is steric hindrance, which is not as complicated as electronegativity. It is really just a measure of the bulkiness of the nucleophile. Indeed, as you would expect, bulky groups in adjacent positions physically limit the nucleophile from reaching its target, thus the decrease in nucleophilicity. Let's briefly now introduce solvent effects as a bridge to the next topic. Increasing the proton concentration of the solvent should also decrease nucleophilicity. Remember, protons are positively charged, so in solution they will shield the nucleophilic elements from their intended reactants. Let's take a look at some of the other solvents now and see specifically how they affect the nucleophilicity of the halogen ions. These three compounds here are examples of polar protic solvents. While we did just say that these solvents will decrease nucleophilicity in general, the extent of their effect will vary for different molecules. Take bromine and fluorine, for example. Both will be shielded by protons in solution. However, while a strong nucleophile like bromine can interact with several protic species and maintain its nucleophilic character, when fluorine, a strong base, interacts with the solvent, it may revert to its acid form, thus neutralizing any nucleophilic character. This next group of solvents describes our polar aprotic options. When subjected to this kind of solvent, our halogen nucleophiles will experience the opposite effect. With no protons to react, nucleophilicity will be directly related to basicity. So we've gone into a bit of detail here about different polar solvents. Why not about nonpolar solvents, however? Note that the majority of the nucleophiles we've seen thus far have been polar. Because a nonpolar solvent will not dissolve a polar nucleophile, there's usually no reaction to characterize, and thus nothing to say about nucleophilicity. Now we are prepared to give electrophiles a proper introduction. Essentially the opposite of a nucleophile, an electrophile is a molecule that is attracted to electron-dense species. Given this definition, and the one we saw previously for nucleophiles, it should be clear that each of these molecules are attracted to one another. This is quite convenient because, as we will see later, the reaction of nucleophiles and electrophiles is a major one on the MCAT. So what makes a good electrophile? Well, if you're thinking the opposite of what made a good nucleophile, then you're right. The more positive a molecule, and thus the less electron density it possesses, the better an electrophile it will be. Often, you will see electrophilicity attributed to a particular atom within a molecule. In the case of a full-on carbocation versus a partially positively charged carbon, the carbocation is a stronger electrophile. When comparing two molecules, both with partial positive charges on the central carbons, electrophilicity is determined by the degree of separation between the partial positive and negative charges within the molecule. For the example of acetone and isopropanol, the carbonyl creates a greater separation of charge between the central carbon and the oxygen atom than does the alcohol, resulting in a stronger partial positive charge on the central atom and therefore stronger electrophilic character. The last piece to review, before we take a look at the reactions between nucleophiles and electrophiles, is the leaving group. When one of those reactions occurs, the nucleophile is essentially taking the place of the functional group already present, termed the leaving group. In order to be a good leaving group, the molecule or atom should dissociate along with the electrons in its bond and be more stable than the nucleophile was before it reacted. Halogens make good leaving groups, especially those farther down in group 7, which have more electron shells and are thus inherently better able to handle larger amounts of electron density. Another category of molecules which make good leaving groups are the inorganic esters, of which phosphate is an example. Water, alcohols, and ethers constitute another subset of good leaving groups. The final category is comprised of the tosylate ion, which can stabilize the extra couple of electrons remarkably well, largely as a product of its extensive conjugation. The concepts of conjugation and aromaticity are a bit out of the scope of this review, but just in general, conjugation refers to the little stretches where every other bond is a double bond. Molecules like this absorb negative charge through resonance, and aromaticity is simply conjugation within a ring. So those were the good leaving groups. Notice we've been spending time comparing the structural elements that affect leaving group quality rather than rattling off names. As we move into the poor leaving groups now, notice the overarching differences between each class. If good leaving groups were relatively stable in their free form, then we can predict that poor leaving groups will be less stable. Indeed, release of a leaving group that is also a strong base will pose another problem. This should be familiar from earlier in the video. If strong bases make such good nucleophiles, then an incoming nucleophile of lesser basicity won't be able to form a bond with carbon. To put it another way, our incoming nucleophile would be a better leaving group than the strong base. Hydroxide and alkoxide functional groups, remember these are good nucleophiles that also happen to be good bases, make up the first batch of poor leaving groups. The next category includes the carbanions. Notice that the members of these first two groups were all mentioned in the section on good nucleophiles. The final poor leaving group we will see is the hydride anion. It's really just a hydrogen atom with a negative charge, but the hydride ion is so unstable that it usually requires an acceptor, as with NAD+ in cellular respiration. So to sum up, in order for nucleophilic substitution to work, the nucleophile must be a stronger base than the leaving group. Thus far, you've been exposed to nucleophiles, electrophiles, leaving groups, and how solvents affect them. But now we're going to put them all together. Out of all the organic chemistry topics that you will see in your prep, this is probably the highest yield and most applicable to the MCAT that you will see. The first of the two substitution reactions is the SN1 reaction, also referred to as unimolecular nucleophilic substitution. In this mechanism, removal of the leaving group is the first step, often due to interaction with the solvent. This is also the rate-limiting step for the reaction because it generates the carbocation intermediate that will participate in the second step. The carbocation, which is sp2 hybridized, will be attacked by the nucleophile to generate the product. Barring any steric effects that make one face of the molecule less susceptible to nucleophilic attack, SN1 reactions yield a racemic mixture of products, one of the hallmarks of this reaction pathway. The second substitution reaction, SN2, proceeds via bimolecular nucleophilic substitution. Again, it is helpful to look at the abbreviated name of this reaction, SN2. It tells you exactly how many molecules will make up the transition state. This mechanism is often referred to as backside attack and depends upon the near total absence of steric effects on the parent molecule. Just as in nucleophilicity, bulky adjacent groups interfere with nucleophile-electrophile interaction, adding an additional hurdle to a reaction pathway that already depends on approach from a specific side. Another key difference from SN1, SN2 products display inverted stereochemistry as a product of this backside attack. Okay, that's the extent of the material this video will cover. Now let's put what you've learned into practice with some sample questions. This first one is testing your knowledge of the generalized nucleophilic substitution reaction mechanism. Before we reveal the answer, let's make sure you're approaching this question in the simplest way possible. First, bromine is a better leaving group than an alcohol. And we know, based on the name of the product, that it does not contain a carbonyl or alcohol functional group, therefore we can eliminate answer choices C and D. Next, imagine the reaction described. We want to determine the reactant that, when combined with an ethyl group, will form 2-methylbutane. Out of the remaining answer choices, only one has the proper number of carbons. It should be B. Before we finish, let's review what was covered in this video. We began by looking at a few classes of good nucleophiles. Then we took a step back and identified the general properties of molecules that make them more or less nucleophilic. Negative charge directly correlated with nucleophilicity, whereas electronegativity and steric hindrance were inversely correlated. For protic solvents, we saw how free protons can interfere with nucleophilicity. We compared the effects of protic and aprotic solvents on group 7 halogen nucleophilicity and introduced electrophiles, which are essentially the opposite of nucleophiles. For the leaving groups, we saw a lot of different molecules, so rather than memorizing, concentrate on their stability in solution. Good leaving groups will be relatively stable in solution, whereas poor leaving groups, often good nucleophiles, will be relatively unstable in solution. We finished with the reactions of nucleophiles and electrophiles. SN1 proceeded via a carbocation intermediate and involved a racemic mixture of products, whereas SN2 gave one main product that displayed inverted stereochemistry as a consequence of its bimolecular transition state. Thank you very much for watching, and good luck in your continued MCAT study.